We'll take a look at slope fields, sometimes called direction fields. Sort of like visual integration. This is what we do. Basically, to every point we assign a gradient. This is how we create one, and it can be quite time consuming to do one. So this was our derivative, y dx equals minus y on x, and we don't really know what it is. Okay. Oh, what is it? We basically create these slope fields. We pick a point, and with every single point we pick, we work out what the slope would be at that point. So for instance, if I picked the point negative 5, 5, substitute that in, I'd come up with a derivative of 1. And when I said it's time consuming, I would do that for every single point on this grid, but there we go. There's the grid completed. So obviously when x is equal to 0, we had 0 on the bottom of the fraction. That's why I put an asterisk there. It's undefined, but there it is. But now, on our number plane, at each of those points, we just draw a short little line, a short little interval of that slope. And we would get something like that. This is why we call it visual integration, because looking at that, I now get a feel for what the curve looks like. I might not know its equation, but at least I know what it looks like. Because remember, each one of these is representing the slope at a particular point. It's suggesting to me it's a hyperbola, some constant divided by x. There's all possibilities that it could be. You see when I draw those curves in, you see how, oh yeah, look, there's tangents to those points sort of matching that pattern. Now, if I wanted a particular solution, the one that goes through the point 2, 2, then it would just be that one there. It would become y equals 4 on x. But how do I work that out? Well, I would plot the point 2, 2, and then I would just follow the direction field. When I draw the curve in, remember, all these things are tangents. So I wouldn't cross the tangent, because it just touches the curve. And if I just draw between those, I get the shape of the curve. And there it is, our hyperbola. Let's just take a look at a few more. So minus x on y, that ends up looking like that. Well, that's suggesting to me circles. There's all possible curves that would have y dx equal to minus x on y. Minus 1 on x cubed would look like that. Wow, what's that one doing? Okay, here's the thing. If the derivative is equal to some function of x, so there's no y in it at all, it's just some function of x, what you should see in the slope field are basically columns that look the same, because they'll all be the same slope. Because you're not substituting in any y values. So it doesn't matter what the y value is, you're still going to get the same thing for every x value. So you will see columns. So if we did not know that, if they just gave us this slope field, we could say, oh, okay, yeah, this derivative must equal some function of x, because what it looks like. But the other things we can tell about the actual function itself. If I see continual horizontal or vertical lines, then we've got an asymptote. So you'll notice here at x equals 0, I mean I haven't drawn in the vertical lines, but that's where it will be undefined. So if it's undefined, I've got a vertical asymptote. Where it's horizontal, it might be y equals a constant number. Of course, that's a possibility. It could be y equals a constant number. Or it's some sort of asymptote. Now this one here, it's more suggesting an asymptote, because you see how it's not completely horizontal all the way, but it's becoming horizontal. Well, there's a family of curves that could be. Y dx equals 1 minus y. This time, the derivative is just a function of y. Now we'll see rows of the same thing. Because we're not substituting any x value in this time, we're only substituting in y values. So it doesn't matter what the x value is, the picture will be the same. So I see a pattern like that, I know, oh, the derivative is some function of y. There's what that one would look like, the family of curves. So we've got this question. The trajectories of particles in a fluid are described by this interesting differential equation, a quarter of y minus 2 times y minus x. What on earth is that function? It's going to be quite tricky to go and find the function. Now here's the slope field. They've drawn that up for us, saved us a bit of time. Identify any solutions of the form y equals k, where k is a constant. So I get to look at my slope field, and I'm just looking for horizontal. Because if the solution is y equals a constant, then the tangent would be horizontal. And looking at that, there it is there. So y equals 2 must be a solution to this differential equation. Now, they've asked us to draw the sketch of a particle that passes through the point -3, 1, which is the point that's been plotted in here, and then describe it as x approaches plus or minus infinity. So I need to go through this point. The tangents are telling me the shape. So now this y equals 2 is not a constant solution. It's going to be a horizontal asymptote. So I know that's going to happen. I've got to come in and get through this point. And so the slopes are telling me, yep, okay, I'm going to come like that. And I just follow the tangents along. And whoop, there we go. I end up with something like that. So I knew it was a horizontal asymptote. I've come down to meet the point I know it goes through, and then I'm just following the tangents. The tangents are basically telling me, head off in this direction. End up with a horizontal asymptote on the right-hand side as well. So it said describe as x approaching plus or minus infinity. Well, then I know y is approaching 2. I even can say, well, from underneath the asymptote. That's what it's doing. So let's just play with slope fields. So 13b, we'll do that.